Hello everyone. In this video, we'll lay out the foundations of linear algebra, why it is vital for data science and machine learning, and the core concepts you need. First, we'll see why linear algebra matters by revealing how it underpins linear regression, neural networks, principal component analysis, and how matrix operations help handle large data sets. Then we will focus on vectors, what they are, how they are represented, and the essential operations like addition, subtraction, scalar multiplication, and the dot products, including their angles, projections, and cosine similarities. By the end of this video, you will have a solid grasp of these fundamentals and you will be ready to tackle real-world data science tasks. Let's get started. We'll start with why data scientists need linear algebra. Then we'll take some real-world examples of linear regression, logistic regression, PCA, neural networks. And then we'll have a quick review of the tools, the libraries that we are going to use for the hands-on demonstrations. Let's get started. So you can run these codes on either Google Colab or your local Anaconda installations. The codes are going to work exactly the same way. So why data scientists need linear algebra? So basically there are 4 mathematical foundations needed for data science and machine learning, including deep learning and generative AI. So these are the linear algebra, probability and statistics, convex optimization, and the foundations of calculus. So in this video series, we are going to tackle linear algebra. So linear algebra provides a mathematical foundation for many core algorithms in machine learning like linear logistic regression, support vector machines, the principal component analysis. For deep learning, we need all the matrix operations for forward propagation and backward propagation. We also need data transformations like dimensionality reduction techniques, feature engineering. That's all needed for the model building. So we are going to work with data definitely, and these data would be present in the form of matrices. Matrices will be basically some number of rows and some number of columns. So rows essentially would represent your data points or samples or records. The features are representing your independent variables, which are attributes which are going to affect the final dependent variable, which is also called as your target. So we are also going to learn about some transformation techniques like rotation, scaling, projections. These are all essentially matrix operations. And then when we are doing some complex model building like neural networks, we will be doing repeated matrix operations. So let's take a closer look on some of these examples. So although we are not going to deep dive into these concepts, but a quick recap of these things will be needed to set up the initial context and a good motivation to learn linear algebra. So in linear regression, we are formulating the problem in the form of y equal to x beta plus error terms. We can plot them as shown in this figure. So we have the independent variable x and the dependent variable which is y, which is essentially also your target. And these are your individual data points. Okay, so each of these data points are represented by some x and some y value. So our objective is to find the best fitting line here, which is drawn in black line here. We want to find out the equation of this best fit line. Okay, this best fit line is given by your formula x into beta. So this is the equation of the best fit line. Let's call it as y hat, where y is the actual target value and y hat is basically the predicted value from the linear regression. Okay, x is the same as the features, the independent variable. And then what is beta? Beta is basically the set of coefficients attached to these features. Okay, so the product of x and beta will give me the predicted value, and all the predicted value will lie along this black line. So essentially this black line is your model, linear regression model, and that black line is represented by x beta. So that's where again you have a matrix of x, which is the features. Beta will again be an array of numbers. So you are multiplying a matrix with an array of numbers, which is your beta, and that is how you are arriving at your y hat, which is also going to be a array of numbers, just like your actual target values. But then the bigger question is, how do we arrive at the beta values? Because we would have the data points x and the actual target values y. Okay, so to get the predictions, we need the beta. So beta is learned from this equation. Okay, the whole job of linear regression is to find the best values of these beta coefficients, which will give you the best fit line. And if you closely look, this is again a bunch of matrix operations. We have x, its transpose. So xt is the transpose of x, that is multiplied by another x. And then you have the inverse operation, that is again further multiplied with a transpose of x, and finally multiplied by the same y. So you see, we have a back-to-back bunch of matrix operations. So similarly, in the case of logistic regression, which is a classifier, okay, we want to find out the equation of the hyperplane, which is the decision boundary, This is my hyperplane or the decision boundary, which separates our classes. So let's say this is one of the class and this is another class. So we want to have a separating hyperplane. We want to find out the equation of this separating hyperplane. And the equation of the separating hyperplane is again very much similar. So you would have a similar x beta kind of thing, where again x will be the features. In this case, one of the features is the height of the persons, and the other x is the weight. So based on the height and weight combinations, we want to identify whether that person is a male or a female. So that classifier line is learned in logistic regression. So again, you would have these operations, and the best values of beta is not obtained by using the equation that I mentioned above. In fact, that is obtained by another process or an algorithm, let's say, called as gradient descent. Okay, let's see what does gradient descent do. So gradient descent helps us to find out the best values of the beta coefficients in the case of a logistic regression. So we will formulate a cost function, which the gradient descent algorithm tries to minimize such that the target values are close to the predicted values. And for each of these beta values or theta values in this case, okay, we have to find out the gradient of the loss function with respect to that variable. Okay, in this case, we are having theta. You can see that this gradient itself is used to update the weights. Okay, so theta k is basically the value of the weight in the kth iteration, and theta k plus 1 is the value of the same weight in the k plus 1th iteration, the next iteration. So we are updating the weights gradually. Okay, so to update the weights, we need this value of the loss function, which is again computed using a matrix operation. So some sort of difference between your target values and the actual values, and that I will multiply with the feature values. Some sort of matrix operation is again used to get these gradients. Okay, and that gradient is again multiplied by a number. In this case, you can see eta, which is a scalar. So this overall gradient descent is again an iterative matrix operations. So next, let's have a look into the principal component analysis. So this can be done via two techniques. We can have the eigenvalue decomposition of our covariance matrix, or we can do the principal component analysis using the singular value decomposition of the matrix. So in both the cases, the concepts are again heavily drawn from linear algebra, eigenvalues, eigenvectors, which we will see in the coming part of this same video, how to calculate the eigenvalues and eigenvectors. And in this case, the entire feature matrix is decomposed into three more matrices, what we call as U, sigma, and V. So we take the sigma matrix, the decomposed part of that main feature matrix, and that is used to decrease the number of features which we are going to use for the model building or represent our entire data. So the whole concept is called as dimensionality reduction. Dimensionality means the total number of features you have in your machine learning problem. Okay, if you have 100 columns or 100 features, then the dimensionality of your data set is 100. So can we represent the same pattern, the same information present in 100 dimensions down to 2 dimensions or 3 dimensions? What is the advantage? If you are able to represent all the information present in 100 dimensions down to 2 dimensions, we can easily visualize the same. Okay, so the immediate application of dimensionality reduction is a visualization of the big data. So that's one of the prominent use cases of dimensionality reduction, other than noise filtering, anomaly detection. So these are also additional use cases of PCA. Okay, so next let's have a look into the neural networks. Okay, in the case of neural networks, you will have neurons in the output layer, you have neurons in the hidden layers, and you have nodes in the input layer. Okay, so the number of nodes in the input layer will be equal to the number of features once again, and the number of neurons in the output layer will be equal to the number of classes in a classification problem, or it will be equal to 1 in the case of a regression problem. So these connections that you see, each of these connections are represented by weights. The same weights which we learned in linear regression and logistic regression, the same weight is again coming up here. Okay, so we will have weight matrices. Okay, so for example, if let's say you have n inputs and you have m number of neurons in the first hidden layer, your weight matrix will be represented by n cross m. Okay, so this becomes another matrix. So in the forward propagation, we will find the values of the output. The values of the output will be compared to the target. That comparison will give me the error. The error gets back propagated, which is again a matrix operation. And then the output of that back propagation is the renewed value of the weight matrix. The weight matrix will keep on changing as we back propagate the errors more and more. Okay, so in multiple iterations, as the model gets trained, the W matrix becomes better and better, such that the predicted outputs become closer and closer to the target values. You can implement this entire architecture of neural network using TensorFlow or PyTorch. So this is a slightly more complicated example of neural network where we have a convolutional neural network. So you have an image which is again a matrix of numbers, and then we have back-to-back convolution operations which are done by passing your kernel. Kernel is again a two-dimensional matrix that you apply on your image. The process of convolution is again a matrix operation. The process of pooling, which is essentially concentrating the feature maps that you are getting by applying the kernels on the images. So that is again a matrix operation. So, and then finally you can see the flattening. Flattening is again a matrix operation followed by a few dense layers. Okay, and again you can see those connections. These connections will have weights. This will again be represented by weight matrices, and finally we'll get the output. So the same output will again be compared with the target outputs. In this case, the output would be probabilities. So you will compare with the target probabilities, you'll get some error gets back propagated, and all the values within these matrices, okay, will be again refined in the process of back propagation. So finally, let's have a quick overview of the key tools in Python that we would be using to regularly work with linear algebra. So one is the NumPy. So NumPy is the main computational engine in Python. All these scientific computations, numerical computations work with NumPy. Okay, so that's your default data type, which will be expected by any machine learning library that you use, especially your scikit-learn. Pandas is just a wrapper over NumPy, which will help you to visualize your NumPy arrays in an easier format. Plus, it will have an additional bunch of functions for quick statistical analysis and data visualization. Also feature engineering, handling missing data, slicing, dropping rows, columns. Those functions are built in within Pandas. You can do these operations very easily. SciPy is again a library which has a lot of functions for advanced linear algebra operations which are not there in NumPy. So it's an add-on over NumPy, you can say, especially when you want to do optimization, work with power series, and you want to work with numerical optimizations, numerical calculus operations like numerical integration or numerical differentiations. And then finally, for plotting, we'll be using Matplotlib and Seaborn. So in this notebook, we have finally discussed what linear algebra is all about, and we have seen some real-world examples. So in the next notebook, we'll dig deeper into the foundations of linear algebra, especially the vector matrices and their operations. Okay, so in this notebook, we'll cover what is a vector, and then what are scalars, what are vectors, and how does it differ from matrices. And we'll do some common vector operations like addition, subtraction, multiplication, and dot products. So let's get started. Okay, so again, I'm importing the NumPy library and Matplotlib for plotting. Okay, so vectors are mathematical objects, and basically they can be represented with a bunch of numbers. Okay, so in simplest sense, you can say that vector can be represented by a bunch of numbers. Let's say 1, 2, 3, 4 is actually a vector. Okay, so imagine that this is just a vector. So it's nothing great. Bunch of numbers is mathematically treated in Python as a vector. Okay, and the number of planes or the space is defined by how many numbers you have in this. So this becomes essentially a vector in 4-dimensional space. It's still a vector, but in 4-dimensional space because we have bunch of 4 numbers. Okay, so how many numbers you have in that collection or that array becomes the dimensionality of that vector. So let's create a vector using Python, and let's try to visualize how a vector looks. So I've created a 2-dimensional vector because there are just 2 numbers, 3 and 4. So the shape you can see is 2. So I'm using the shape function from NumPy to get the shape of the vector. Similarly, in this vector v3, I've got 3 numbers, 1, 2, 3. So there are 3 numbers, and you can see the shape is 3. So essentially, this becomes a vector in 3D space. Okay, that's the geometric interpretation. Let's have a visualization on how these vectors look in 1D, 2D, and 3D spaces. Okay, so let's say we have a vector u, which is given by 2, 3. Okay, so how do I visualize this vector u? Okay, so let's say this is the origin, which is 0, 0. This is my x, and this is my y-axis. Okay, so the intercept in the x-axis is 2 units. So let's say this is 1 and 2. Okay, so this is the intercept for the x-axis, and the intercept for the y-axis is 3 units. Okay, so this is 3. So I'll just mark this point here. Okay, that point. So now if I draw a straight line from the origin till that point, okay, that becomes my vector u. Okay, so this becomes my vector u. So this u is represented by this line from the origin until that coordinate point, which is 2, 3. So that's vector in 2D. Okay, so a vector in the n-dimensional real space is essentially an order list of n real numbers. You can see. So a vector in 3D will be represented by a bunch of 3 numbers. Okay, so this is a quick Python code which helps us to visualize two vectors here. So I have got a vector u and a vector v. So the vector u, you can see, is represented by 2, 3. So 2 units in the x-axis and 3 units in the y-axis. So I'm just joining with a line from origin to that 2, 3. And the other vector is given by -1, 4. So the intercept in the x-axis is -1. You can see that -1. And this is 4 units in the y-axis. Okay, this is the 4 units and this is 3 units. 3 and this is 4. So this is 2, 3 represented by u and this is your v. Now let's see the difference between scalars, vectors and matrices. So scalars are essentially single numbers, a single number like the value of pi 3.14 or a number 2, 5, 5,000, 5 million. A single number, however large, small, negative, fractional, is still a scalar. Okay, it could be integer or float. So vector, as we have seen, is a one-dimensional array. So it's a bunch of numbers, and the number of numbers in that array can be any large. Okay. So when you have a bunch of numbers in a two-dimensional grid, okay, with the shape, let's say m rows and n columns, that is where we encounter matrices. Okay. So a two-dimensional grid of numbers will be called as a matrix. Otherwise, if it is a single-dimensional array of numbers, that's a vector technically. And if you have a single number out of it, that's a scalar. So essentially, you can say that vector is a collection of scalars. Okay, and a matrix is also a collection of vectors. Okay, so I have displayed here a vector in 3D. So you can see the intercepts of this vector OP is 2 units in the x-axis, 3 units in the y-axis, and 5 units in the z-axis. Okay, and matrix, as I said, it's a grid of numbers. So you have m rows and n columns. Okay, you can represent it by square brackets or parentheses. Both are completely fine. So what are the typical uses of scalars, vectors, and matrices in data science? So scalars, as I said, these are single numbers. So for example, in the gradient descent, we talked about that eta, which was the learning rate or the step size. So that is a scalar. Most of the hyperparameters that you use during model training in deep learning, like number of epochs, is a scalar. And the batch size is a scalar. Number of neurons in a hidden layer is a scalar. The number of neurons, the number of hidden layers, okay, it's also a scalar. The number of neurons in the output layer is also a scalar. So a lot of scalars we encounter. Vectors, these are data points with multiple features, okay, or you can have the model parameters. So you remember that beta coefficients, that beta hat which we calculated by multiplying x transpose x, taking the inverse, and then again multiplying it with x transpose and y. That beta hat is essentially a vector. So that will contain all the beta coefficients for each of the features in your linear regression problem. Matrices, as you see here, I have displayed a entire data set, a Boston house pricing data set, where again in this case, each of these features, these are all features, are vectors. So this is one vector, this is another vector. So these are called as column vectors. So each of them is a column vector. What is a column vector? A column vector will have all the values in exactly one column. It can be n number of rows, but all the values will be in a single column. So each of these features is essentially a column vector. Now if you see, each row here represents one data point. This is one data point, and that one data point is essentially a row vector. Okay, so vectors can be further classified as column vectors or row vectors. A row vector will have all the values exactly in one row. Column vector will have all the values exactly in one column. So features are column vectors, and individual data points or samples or records will be row vectors. And the entire data set will be essentially a collection of these column vectors of features or row vectors of data points. So this entire thing is your matrix. This is also called as your feature matrix. Okay. Now let's have a look at the common vector operations. Okay, we'll start with the vector addition. So vector addition is always defined element wise, which means that the total number of numbers in the vectors must be exactly the same. Okay, I'll give an example. So let's say you have a vector u1, u2. So these are the individual numbers in the vector u. You have n numbers in this vector u. Similarly, you need to have exactly n numbers in the vector v so that we can add the vector u and v. Okay, so what is essentially being done is the first number in u1 is added to the first number in v1. The second number in u is added to the second number in v, and so on. That is exactly the reason the total dimensionality of each of these vectors must be exactly the same for this element-wise addition to be successful. Otherwise, you will get an error, and that is mathematically invalid operation. So for subtraction, very similarly, the first number in U will be subtracted by the first number in V, and so on. You can see here. So let's do this in Python. I am defining U as 124 and V as 352. And you can see the addition of 1 and 3 is 4. And similarly, addition of 2 and 5 is 7. And finally, the addition of 4 and 2 here is 6. That's how I get the addition of two vectors, U and V as 4, 7, 6. And for subtraction, the operation is very simple, U minus V. And you can see that 1 minus 3 is minus 2, 2 minus 5 is minus 3 again, and 4 minus 2 is 2. That's how I get this vector. So the addition and subtraction of two vectors will also result in a vector. Please understand that the resultant is also a vector with the same dimensionality. How do I visualize this addition and subtraction operations? This code uses the quiver plot to represent the vectors, and let me run this code. So you have this vector U represented by this blue arrow line. So this is vector U, this is the vector V. So the vector V actually does not start from here. So the vector V has been translated. So vector U is given by 3, 2. There are 3 units, 1, 2 and 3 units in the x-axis and 2 units in the y-axis. So this point is 3, 2, and vector V is defined by 2, 4. So essentially 2 units in the x-axis and 4 units in the y-axis. So we are looking for a line from 0 going up to 4 this way. This is your original V given by 2, 4. So what I have done here is translated this vector such that the starting end of this V coincides with the ending of U. Okay, so I'm just superimposing by translating this. Okay, so this V is now translated such that the starting point of V coincides with the ending of U, and that's how you have this V, and the point where this V ends. Now I am connecting the starting point of U to the ending of this translated V by a green line. That's the entire vector addition U plus V. So the resultant of U plus V is represented by this green arrowed line, okay, which starts with the starting point of U to the ending point of V. So that's the addition vector. So similarly for the subtraction, I have translated this vector V so that the V has been inverted. So we can represent U minus V operation as U plus of negative V. So negative V means you invert the direction of V and then align it in a way that the starting point of V, so this is essentially minus V, this is still U. Why is this minus V? Because we have inverted the direction of V, okay? And then we aligned it in a way, so this was your original plus V, and we inverted the direction and then translated it here. So this green line now represents U minus V. Okay, so now let's have a look into the scalar multiplication. So scalar multiplication means you are multiplying a scalar with a vector, okay? That essentially scales that vector. Now that scaling is done by a scalar, of course. If the value of the scalar is less than 1, you are essentially shrinking the vector, and if the value of the scalar that you are multiplying is more than 1, then you are enlarging that vector, okay? So C is the scalar, V is the vector, and when we multiply the scalar with the vector, each element of that vector V, vector is a bunch of numbers, so each of the numbers within that vector gets multiplied by that scalar C. So you get CV1 and then CV2 and then so on until CVN, right? So let's have this code here. So my vector is represented by 3, 2. When I multiply 2 here, so 3 gets multiplied by 2, we get as 6, and then 2 gets multiplied by another 2, which is now giving me 4. So that's how we represent. I have got 2 more scalars here. One is a scaling by a factor of 2, and then this is scaling by a factor of half, okay, and negative. So basically the direction will also be inverted. So let me run this. So your original vector is this. This is your origin, and this is the original vector, okay. That's basically 3, 2. Yeah, that's 3, 2. That's our vector U. So when I'm multiplying it by 2, we get the red line. So essentially we just increased the length of the vector, okay, 2 times. So that's your 2U. And when we are multiplying by negative 0.5 times U, means I am first reversing the direction of U and then making it half. So multiplying by 0.5 means multiplying by half. So you are decreasing or shrinking the length and also reversing the direction. That's the effect of negative multiplication and multiplying a scalar which is less than 1. Now let's have a look into the dot product. Okay, so dot product is very fundamental and very important concept in linear algebra. So in the dot product case, we will multiply each element of the vectors u with their corresponding elements in the vector v and then adding them up. Okay, so for example, here we have u represented by u1 and u2 and v represented by v1 and v2. So the dot product of u and v will be given by u1 multiplied by v1 and then added to u2 multiplied by v2. So if you have multiple such numbers, that would have been plus u3 v3 plus u4 v4 plus and so on. Okay, so this is what it looks in 2D and that will go in n-dimensional space the same way. How do I visualize that dot product in a geometrical sense? So for that we need to again visualize these vectors in the 2D space. So let's say I have my vector, this is given by u, this is given by vector v, okay, and this is the theta angle between them. So essentially I'm talking about the cos of theta, where cos theta is nothing but the angle between them, these two vectors. So this is the norm of u, this is the norm of v. Norm is given by this notation, this is called as norm of u. So norm of u is represented by square root of u1 square plus u2 square plus and so on. So whatever be the number of elements present in u. So you take the square of those elements and then you add up. So finally you take a square root. So it's basically square root of the squares of the sum of the individual elements in that vector. That's called as L2 norm by default. Okay, so this is your norm. So similarly you take the norm of v, multiply them and then also multiply the cos of theta. That will give you the dot product of u and v. A bit complicated, but it's very easy when you visualize them. So here is a code snippet which you can use to visualize. So I'm defining my vectors u and v here. So u is 2, 3 and v is 4, 1. So dot product between them is 11. So essentially you can see 2 multiplied by 4 is 8 and 3 multiplied by 1 is 3. 8 plus 3 is 11. That's how we get this 11. There is a concept of element-wise multiplication also. In the element-wise multiplication, each element of the vectors u and v get multiplied but not added. Okay, so the net dimensionality of this product, this element-wise multiplication, will be equal to the dimensionality of the vectors u and v. Okay, so let me show you this. So this is 8 comma 3. That's what I said. You do not add this 8 and 3. So if you add all these numbers, then what you get is the usual dot product. Okay, so we have both the concepts and both the uses in data science. How do you find the norm? For that we will be using the norm function from the linear algebra module in NumPy. So this is how you get the norm of u and the norm of v, and then I am finding the cos theta, which is nothing but a dot product value divided by the product of the two norms. And once we have the theta, we can take the cosine inverse function from NumPy to get the theta in radians, or you can convert that theta in radians back into degrees. Okay, so let me calculate all these numbers. So this is the norm of u, norm of v, and then we get the cos theta is 0.7934 and the angle between the u and v is 42.27 degrees. Okay, so interesting thing is the interpretation of this angle. If this angle is less than 90 degrees, then the cosine of this angle will be between 0 and 1. Okay, cos 0 is 1, cos 90 degrees is 0. Okay, and if the angle between these two vectors is greater than 90 but less than 180, then the cosine of this theta will be negative. Okay, so essentially you can visualize the angle based on the value of the cos theta or the other way around. Okay, cos of 180 will be minus 1, which essentially means that these two vectors are pointing exactly opposite to each other. That would be cos of 180 degrees minus 1. But what is the physical meaning of this cosine? Cosine helps us to also understand the similarities between these two vectors. Okay, so if these two vectors are very similar, the cosine of the angle between them will be closer to 1. So you'll get a number, this number will be closer to 1. So let's say if the cosine of the angle between two vectors u and v is 0.95, then these two vectors are very similar in terms of the information that they carry. Okay, whereas if you have two vectors which are perpendicular to each other, means then the cosine between them will be 0, cos 90 is 0, which means that the information carried by these two vectors are explicit to each other. I mean, they are non-overlapping piece of information. Okay. So no part of the vector or no information carried by u1 can be replicated by u2. So they carry unique information. Let's also visualize the dot product and the angle. So this is the code. This is your vector u, this is the vector v, and the angle between them theta, we already calculated it to be 42.3 degrees. So finally, we come to the concept of cosine similarity, which we have already quickly discussed. So cosine similarity is given by reversing the formula for the dot product, essentially. So you have the dot product between the vectors u and v in the numerator, and the product of the norms of the vectors u and v in the denominator, and that is equal to the cosine of the angle between these two vectors. So cosine similarity is essentially represented by the cosine of that angle. So the value of the cosine similarity again goes from -1 to +1. If the value is closer to -1, then these two vectors are diametrically opposite to each other and they carry completely reverse or inverse information. And if the cosine theta or the cosine similarity is closer to 1, then the information carried is very similar. So in machine learning, we use this cosine similarity concept very much when we are talking about text embeddings and so on. So finally, let's have a quick summary. So in this video, we talked about what a vector is. We learned about different types of scalars, vectors, and matrices. We also learned about the vector operations, the dot product and the geometric meaning, the visualizations of all this. In the next video, we'll talk about matrices in more detail. We'll be doing matrix operations like addition, multiplication. We'll also talk about special matrices and then determinant, inverse, and all these operations, which form the backbone of most of the data manipulation and processing tasks in data science. Thank you for joining me in this video. For more such content, do like, share, and subscribe.